Hello, everybody. Welcome to a new episode of the Dissenter. I'm your host, Ricardo Lopes, and today I'm joined by Dr. Tim Maudlin. He's professor of philosophy at New York University. His interests are primarily focused on the foundations of physics, metaphysics, and logic. His books include Quantum Non-Locality and Relativity, Truth and Paradox, and the Metaphysics within Physics. And today we're going to focus mostly on the philosophy of physics. So, Dr. Maudlin, welcome to the show. It's a pleasure to everyone.
Thank you. It's good to be here.
Okay, great. So, perhaps just to introduce people to the topic, what are some of the questions that the philosophy of physics deals with? Because I would imagine that on the one hand, we have the science, physics itself, and then philosophy of physics. I mean, they probably overlap in some aspects, but what are the questions philosophy of physics is interested in?
Well, generally, when you do philosophy of science, there are kind of two directions this can go in. One is sometimes the science will have results that bear on longstanding philosophical questions. So you say, all right, philosophers have been interested in the nature of space and time forever. The theory of relativity presents a different possibility. Let's sort of take that on board and see what effect the science has on long-standing philosophical problems. The other direction is the other way. It's to say sometimes the science is the subject of philosophical analysis. So the philosophers come in and say, well, what's really going on in this theory? And you don't rely on what the physicists tell you there. You're more in the position of trying to push forward from what the physics would do. There's no general answer in philosophy of physics because it goes different ways. For example, in the theory of space and time and relativity, the experts in relativity really understand the theory very well, and you learn a lot from talking to them. In quantum theory, if you ask, well, what is that theory telling me about the world? The physicists don't have a clue. I mean, this is just not, that theory is not on a solid conceptual foundation. And so it's much more the case that as it were, from the philosophical side, you're pushing and trying to understand the theory in a way that the physicists can't exposit it. Now, it's odd to call that philosophy. You might say, well, why isn't that just physics? And the answer is it is just physics. It's a piece of physics. It's a part of physics that has largely been abandoned by physics departments. And so physicists interested in the basic question, for example, what does quantum theory tell you about the world, which sounds like a question of physics, which it really is, they get exiled to the philosophy department. So that's, you shouldn't take too much from the fact that people are in philosophy departments. And I mean quite literally, David Albert at Columbia got his degree in theoretical physics from Rockefeller University and was interested in foundational questions, and he really could pursue them in a philosophy department in a way he could not pursue them in a physics department. So that's why he's in the philosophy department.
That's very interesting. So, are there any questions that physics is not well equipped to answer, and that perhaps philosophy of physics would be better equipped to deal with them? For, I don't know, you mentioned some foundational questions. Is it that we have to do philosophy to really arrive at the definite answer, let's say, and we can't really just do it through physical data or
Right,
knowledge coming from
absolutely.
physics?
Yeah, it's exactly like that. I mean, let's take a very simple question. If you ever took basic physics or more importantly, basic chemistry, you learned about electron orbitals, and probably in the book, you remember there were these pictures of the s orbitals and the p orbitals and these dumbbell-shaped kind of d orbitals and so on, right?
Right.
So it's part of the science text presents that picture. But then you ask a very simple question. So what's it a picture of? What's being depicted in this picture? right? What is an electron orbital? I mean, the words electron orbital suggest there's an electron that is orbiting. But mostly the physicists will tell you, no, 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 there is no electron that's orbiting. And then you sort of get this talk about, oh, the electron's popping in and out of existence. So here, I mean, here are three possibilities. Let me just lay them out. One is that, yeah, there's really an electron, a little tiny electron, and it's orbiting. And the picture is as if you took a long photograph with a long exposure and tracked where it went over a long period of time, right? You'd get this orbital.
Right.
Here's another picture. Well, no, electrons are not little particles that are moving, but they somehow pop in and out of existence. They're like, you know, they just are this fuzzy kind of thing. And again, if I took a long-term photograph of it over a long period of time, it would pop in and out in these different areas. Here's a third possibility. You say, no, no, no. The electron is neither a little moving particle, nor does it pop in and out of existence. It itself is just spread out. And this doesn't require any time-lapse photography. This is a picture of how the electron is spread out. Those are very different accounts of what that's a picture of. And the physicists will not answer the question which of the three or some other besides the three is the right way to think about it. Schrodinger said something very beautiful about this. He said in a letter, he said, there's a big difference between a shaky or out of focus photograph and a sharp picture of cloud banks, right? Because in one case, the shakiness is coming from you, and in the other case, it's an indefiniteness or a spread outness in the thing itself. And Schrodinger was complaining that physicists just don't make this distinction. So this is you've got a clear mathematical object that's being used as a representation. But the question is, what does it represent? And that's not a question physicists are equipped to answer from their training.
Mm-hmm. I understand. What about quantum mechanics? I mean, where do you place quantum mechanics in the broader context of physics?
Well, quantum mechanics has a dual role. At a practical level, almost all of physical behavior that we understand through quantum mechanics. The only exception at this point is gravity, because there is no theory of quantum gravity, and that's taken care of by the general theory of relativity. And quantum mechanics, we know how to get predictions out of it, and the predictions are tremendously accurate. So we know it's on the right track, and there's all kinds of very surprising phenomena that you can predict well with it. So at that level, it is, in some sense, the most important foundational theory in physics. On the other side, it's the least understood. Unlike general relativity, special relativity, where if you work with those theories, you come to understand very well what they're saying about the world, there is no agreement at all, zero agreement about what quantum mechanics is telling us about the world. And so it is the most ill understood or mysterious or dark, conceptually dark part of physics, at the same time being the most foundational part of it.
Yeah, and do you think that in order for physics to have sort of a core theory from which all other things would derive, we would need to have a theory that would integrate quantum mechanics with general relativity?
Sure. I mean, because nature does it, right?
Yeah.
I mean, you know, in stars, in heavy stars, you have very strong gravitational effects and you have very strong quantum mechanical effects. And somehow or other, nature manages to deal with them both at the same time. So there must be some way to reconcile those theories, bring them together and have them operate conjointly, because they do operate conjointly. So there must be a theory.
Mm-hmm. What about the specific case of string theory? I mean, is there a good evidence to support it? Because I know it's a very contentious topic in physics and philosophy of physics. So what is your take on that?
Look, the history of string theory is extremely weird. And what I'm about to say is not at all controversial. The basic idea, you sort of say, well, our normal picture of an electron is a little point particle that can just move around, right? The only degree of freedom it has for it is to change its location. And then somebody says, well, what if instead of that, it's a little one-dimensional object, right? Rather than being a zero-dimensional object, a point that moves, what if it was a one-dimensional object, like a string that moves? So in addition to moving around, it can vibrate. Okay, that's a kind of decent question. Now, originally that idea came up trying to explain a certain known physical phenomenon. And people worked on some of the math. It's very difficult mathematics. That particular phenomenon turned out not to be explained that way. A completely different explanation was proposed and accepted. But the math had already been created. So then some people were playing around with the math, right? That sort of the math took on a life of its own. And then after a while, some people said, hey, maybe we can use this math to solve these other more fundamental problems, to give what was called a grand unified theory, or a theory of everything, ultimately. And then string theory sort of took off in this other direction. And then the math got more and more complicated, and you got M theory, and you got these membranes and all this stuff. I mean, there's a big, long mathematical story. Then you ask, okay, but is there any empirical reason to believe this to be true?
Right.
And from the beginning, the answer was no, but that's okay. You know, you're exploring a theoretical possibility. That's fine. As time went on, it got worse and worse because there were the theory is what's called a supersymmetric theory, which means that for every particle we know about, a quark, a neutrino, a photon, an electron, the theory postulates there'll be a so-called supersymmetric partner. Like, so you have the photino and, everybody, gluinos and all these things get their name. And this is part of the theory, this supersymmetry. And if there were all of these other particles, twice as many as we were aware of, you'd sort of say, well, why don't we see them? Why haven't we found them yet? And the answer to that was, well, they're too heavy. If you try and create particles in a particle accelerator, you need enough energy to create them. And originally people said, well, yeah, there are these supersymmetric partners, but they're too heavy, and they had kind of estimates for where you might find them. And then as time went on, you kept getting bigger and bigger colliders. You had the Large Hadron Collider at CERN, where they found the Higgs particle. And people kept saying, well, maybe as we ramp up the energy, we'll start to see evidence of these supersymmetric particles. And it never showed up. And so just it's like the frog in slowly heating water. You can't draw a line and say, well, we know this theory is wrong. But every time they ramp up the energy and they don't find anything, you say, well, it just looks like we really have no evidence for supersymmetry. The other kind of thing people were looking at, and this is also a prediction of supersymmetry, is that the proton will not be stable. There'll be proton decay. And people have been looking at that for decades and decades, these big, huge things of water underground that they monitor, because if the proton were to decay, you would get these products coming out that would have a very clear signature. And again, I remember when they started those things, and it was, well, yeah, it'll take a year, it'll take 2 years, because these decays will be very rare, but we'll see them, and after a year, nothing, after 2 years, nothing, after 5 years, nothing, after 10 years, nothing. And as time goes on, you just say, well, no, it just looks like the proton is not unstable. So that was a kind of prediction, not a precise prediction, but a kind of prediction that you looked at and you're not seeing it. So as time goes on, you'd say the evidence for supersymmetry isn't there. And string theory is a supersymmetric theory, so it's in trouble.
Mm-hmm. What about other things that derive from string theory? Because I know, for example, that at least some people propose that reality would have to have 11 dimensions or something like
Well,
that.
yeah, Right, just for the theory to mathematically be consistent, you can't do it in 4 dimensions.
Okay.
And there are different ways to do it. And originally it was 21, and then they got it down to 11, or they got it down to 10. And there are just different kind of ways of implementing this idea, but you can't do it in 4. And then you say, well, gee, isn't there pretty good evidence against that? Because it looks like there are only 3 spatial dimensions and 1 time dimension. So aren't you dead? And then you say, no, no, no. There could be these other dimensions that are compactified, that are, as people say, if you look at a long distance from a garden hose, you'd say, oh, it only has 1 dimension. You move a position along the hose. But then if you go down and look at it very carefully, there's this other wrapped up dimension. It's really a 2-dimensional object. It's a tube. And you not only have a position this way, but you have a position this way around the diameter. And you can do that with more dimensions. You can just add as many dimensions as you want and then compactify them. And this gives rise to these things called Calabi-Yau spaces, and there's a lot of math in that too. So the dimensionality was never a real problem in the sense that they could explain why it's not evident that there are these extra dimensions, but they're still there.
Mm-hmm. And since we're talking about dimensions, is time really better understood as another dimension or not?
Well, there's an implication in just another dimension, which I think is misleading. Time clearly is a dimension in the sense that things are located at different places in time, as it were. And if there's an event, right? So an event, like I just snapped my fingers, if I want to locate that event, and again, let's forget about extra dimensions, but just in everyday life, if I want to locate that event, I have to give you 4 numbers. I have to give you a latitude, a longitude, right? That would put you, as it were, in New York, an altitude, then you're on the 5th floor, and a time. Right? Because that event took, I have to give you a 4th number to locate that event. So that's another dimension. I mean, that's just trivial. That doesn't mean that time is just another spatial dimension. When you say, is it just another dimension, it sounds like, oh, you're just adding another spatial dimension. No, you're not. It's not like space. It's not space. We know what a 4-dimensional spatial object would be like. And nobody thinks space-time is like that. It doesn't have the same geometry. So yes, as it were, trivially time is a kind of dimension, and equally trivial, it's not a spatial dimension. Time isn't just more space.
Mm-hmm. But when we talk about time as another dimension, does it have anything to do with how we experience time, or is it a completely different thing?
Well, we experience time as going forward. I mean, the main difference between time and space is that we don't understand space to have any intrinsic directionality, right? You would not say that space, as it were, runs any more east to west than west to east, or north to south than south to north, right? Those are different directions. But you wouldn't say space itself is directional. But we do say time goes a certain way, right? Time goes from past to future, period, end of story. And we all understand what that means. And we occupy different positions in time as time passes, so that it's a dimension. That is, it has lots of locations that are ordered. Yeah, that's kind of trivial. Again, there's one way of hearing these things that make them sound kind of astonishing. The sense in which they're true, they're not astonishing. They're just everyday common sense.
Yeah, because I've heard some people, I don't know if this is a position held by physicists in general or if it's more of a fringe position, but I've heard some people saying that perhaps time as we experience it running from in a particular direction from past to future doesn't exist, and all of we have a different I mean, how should I put it? It's like different photographs superimposed one
Yeah,
upon
yeah,
the
yeah.
other.
I look, yes, you will find physicists saying all kinds of things about this, and
Okay.
the idea that there really is no directionality to time is something many physicists would say for very bad reasons. I think there's actually no good reason that exists. You can see how that would completely contradict our experience of time, right? To say it doesn't have a direction. And I actually think that the source of this is, again, and this is what a philosopher is maybe better attuned to, bad terminology. So there's a feature that a law of physics can have that's called, the name of it is time reversal invariance. And many physicists sort of say, oh, if the laws of nature are time reversal invariant, then there's no direction of time, right? That's sort of, you just go from the one to the other. But then if you ask, well, what is time reversal invariance? It's not what it sounds like. So let me give you another example. You can do an experiment, set it up in the lab, and then you could imagine, well, what if I did a mirror image experiment? So if here in the actual experiment, the particles are going around in this way, right? So looking from above clockwise. In the mirror, they would be going counterclockwise, right? If you looked in a mirror from above, they would be going counterclockwise. So you say, well, gee, what if I did an experiment? I took an experiment that I've done, and I set it up in the lab mirror imaged. Would I get the mirror image result? Would everything in the mirror image lab, as it were, happen as if it really were in a mirror? That's called parity, that changing of left for right, if you will, or changing the directions in space is called parity. And some theories are parity invariant. So they tell you, look, if this is what will happen in this experiment, if you set up the mirror image experiment, you'll get the mirror image result. That's called parity invariance. Now, it turns out, as a matter of fact, that doesn't hold. This was a great, very important discovery, that parity is broken. It just turns out not to be true. We've known that for a long time. Now, someone says, well, what about time reversal invariance? So I just want you to see the analogy. You've got parity invariance, and you say, here's my original experiment. Now, here's the other experiment. Does it come out in a certain way? Now, what about time reversal invariant? Okay, I go into the lab, and I do an experiment, and I get a result, and then someone says, okay, why don't you set up a time reversed, why don't you do that very experiment backwards in time? And, you know, the experimentalist is going to look like you're crazy. What do you mean do it backwards in time? I can't do it backwards in time, right? How can I do that? How can I reverse time? I can't reverse time. And then you say, oh, no. Really what I mean is reverse velocities. Reverse time derivatives. So if in this experiment an object is traveling with this velocity, right, going this way, in the new experiment, reverse the velocity and have it go that way. All right? And so there is an operation that is called time reversal, but that's not what it means. It just means velocity reversal. That doesn't mean time doesn't have a direction. In fact, this velocity is different from that velocity. And, you know, and they're different because of the direction of time. Because in this one, earlier it's here and later it's here. And in that one, earlier it's here and later it's here, right? So the very difference in the two experiments would be a difference relative to time direction. So what happens is, because what is really velocity reversal is called time reversal, which was just a bad idea, people say, oh, if the physics is time reversal invariant, then there's really no direction of time. That doesn't follow at all. On top of which, in quantum mechanics, it isn't time reversal invariant. that's actually associated with it not being parity invariant either. So this entire thing falls apart. There's nothing there. There's just literally nothing there. People have convinced themselves by very bad arguments that time doesn't have a direction. And I really don't think there's a single empirical fact, theoretical fact, or anything you could point to that suggests time is not directed.
Mm-hmm. And with all of that in mind, do you think it will ever be possible for us to have time travel?
Well, now let's put on our philosopher's hat.
Sure.
What do you mean by time travel? Here's something you could mean, that you can go from one point in time to a different point in time. Not only is that possible, it's actual. Not only is it actual, it goes on all the time, right? We are right now traveling forward in time. And the future is on the way, and I guarantee that in 10 minutes, we will be 10 minutes into the future, okay? So we are constantly traveling, as it were, insofar as one makes sense of such a thing. We're constantly traveling forward in time. So not only is time travel possible, it's inevitable. You can't stop it. Now, so what do people mean when they say is time travel possible? They could mean, well, by continuing to go forward in time, can I ever get to the past? Okay, That's a question. I think the answer is no. You could actually have mathematical models of general relativity where the answer is yes, right? As a piece of mathematics, you can sort of imagine time as it were curling back on itself and closing on itself like a big cylinder. And you get what are called closed time-like curves, which are just what they sound like. They're curves that you always go forward in time along, but they close, they come back to themselves. Models of the theory of general relativity exist that have that property, but that doesn't mean it's physically possible. There are models of general relativity that have the property that you can't even orient time. So if you think of a Mobius strip, where you take the strip and twist it and glue it back together, that's non-orientable, because if I start on it with an arrow pointing this way and I go around, the arrow comes back pointing the other way. So it doesn't have a mathematical property called orientability. You can have solutions to the equations of general relativity that are not even temporally orientable. Nobody takes those seriously as physical possibilities. Those are just mathematical things that don't represent physical possibilities. I think the same thing about closed time-like curves. I don't think there's a reason in the world to think that it would be possible to go forward in time and come back to where you started. There are mathematical models that allow that, but I just think they're ruled out by the nature of time itself.
Mm-hmm. So does physics itself have anything to say about the nature of reality? I mean, just with physical data, can we answer questions like what is real?
Well, you just asked two different questions.
Oh, okay.
And we better keep them separate. One
Okay.
is, does physics have anything to say about reality? And the other is, does data have anything to say about reality?
Okay.
Physics better have, because that's what a physical theory is, right? A physical theory is a proposal for what physical reality is. So, is there space and time? What structure do they have? What kind of particles are there? What are those particles like? All of those are questions about physical reality, and a well-constructed physical theory will answer those questions, right? And this goes back to talking about the electron orbitals. In a well-constructed physical theory, if someone presented it and gave me a picture of an electron orbital, and I say, yeah, but what's that a picture of? Is that a little particle that's moving around through time, or a particle that's popping in and out through time, or is it something that's spread out? The theory should answer that question. Oh, my theory says this. Another theory might say something else. So yeah, a physical theory is a proposal about physical reality. But then the question is, can we know which physical theory is right? There we appeal to the data, but we have this ubiquitous problem of underdetermination of theory by data, which has been noticed philosophically forever. The same data can be accounted for in different ways by different theories. So typically, the data alone will not pick out a unique theory. And so you're left, on the one hand, you want to say, okay, give me as many theories as you can that are consistent with this data. And then you can ask, well, gee, are some of these theories more plausible than others on the basis of the data, on the basis of simplicity, on the basis of some other conceptual considerations?
So what is the relationship between physics and metaphysics?
Metaphysics, and again, this is just has a very simple answer. Metaphysics historically is just what Aristotle called the theory of being qua being, meaning the theory of what exists merely insofar as it exists, right? Different kinds of existence. So Aristotle would say there are different kinds of existence. A substance like Socrates exists in a certain way. A quality like Socrates' tallness exists, but exists in a different way, right? Socrates' paleness exists because Socrates is pale, but his paleness has a different kind of existence. And so metaphysics is just the most general high-level theory of what exists. Some things that exist appear not to be physical at all, like if you think numbers exist, right? They're not physical. But lots of things are physical, right? Computers are physical. They have a physical existence. There should be a theory of the nature of physical existence. And physics should be that topic. And so it's part of metaphysics. It's not all of metaphysics. Because at least if you're, say, a Platonist about numbers, you say, okay, those are real things that exist, but they're not physical. But physics is just a subclass of metaphysics. It's a theory of certain things that exist, talking about their nature.
But when we're trying to decide what exists, so for example, on the one hand, we have our own perceptual experience, and on the other hand, we have how things work at a subatomic level, for example. So, and we know that what we experience through our senses, at least doesn't correspond exactly to what we find when we go and study things at a more microscopic level, for example. So, when we're trying to answer the question of what exists, is there a trade-off between those two sets of things?
Well, trade-off isn't quite the right word. What we have is the issue of what kind of evidence do we have for theories that make claims that go beyond the evidence. So a theory of microscopic structure, right? The atomic theory of matter, which already Democritus imagined, you can't verify that theory just by opening your eyes and looking around you, right? You see tables and chairs, but you don't see atoms.
Right.
Eventually, we could do experiments or notice certain phenomena and say, hey, these phenomena would be really well explained if matter had an atomic structure. And so we say these phenomena provide good reasons to believe, evidence in favor of the atomic theory of matter. And, at this point, if someone questioned the atomic theory of matter, you'd say they were crazy, right? You'd say, no, our evidence that there are atoms and hydrogen and, the entire periodic table and, basic chemical bonds and things like that is so strong and so ubiquitous and that you'd be insane to think that we don't have every reason in the world. That's, the evidence for that has become overwhelming, but the evidence never was literally, oh, I see, I see the atoms. So that's just the general question we have in philosophy of science about confirmation theory, right? If we have certain evidence, how strongly does it support various different theories?
Mm-hmm. But if we have, for example, a chair and the atoms that compose the chair and their interactions, can we say that both the atoms and what we experience as a chair, they are both real?
Well, look, I think we all know at this point the atoms are real, the chair is
Okay.
real. It's a collection of atoms that have been chemically bonded to each other in a certain configuration. That's what a chair is. I mean, you know, the, Plato always asked the question, the fundamental philosophical question, the single fundamental philosophical question is, what is it? Right? In Greek, tiesti, right? What is courage? What is justice? What is a chair? Okay, a chair turns out to be a collection of atoms that have been bonded together chemically in a certain kind of structure. That's what a chair is. Now, you can then ask, well, what about our experience of the chair? And if you then mean conscious experience, all right, now we're into the mind-body problem. And now we have real trouble because nobody knows how to solve the mind-body problem, right? I don't know how to give an account of my conscious experience of the chair. What I believe is that my conscious experience of the chair reflects certain macroscopic facts about the chair, right? The chair really does have a shape like the one it looks to me to have. And it really is rigid the way it appears to me to be rigid. And, it's black and so on. So those properties are not conscious, they're not subjective properties. And I think I can explain those properties through physics. I do think I know I have experiences. I don't know how to explain my experiences through physics. That's the mind-body problem.
Mm-hmm. And is there any way of addressing that problem through science or not?
Not that I know of. I think the mind-body problem, I mean, it's called the hard problem of consciousness because it's a hard problem. And it's really hard, not because we don't know the answer, but because we can't even imagine what an answer would look like, right? So if you contrast that, if you go back to ancient Greece and Democritus says, look, I think matter is made of atoms, little shaped atoms that have hooks and eyes and bounce around. You say, well, I don't know if your theory's true, but at least I understand if it were true, how it would explain what I see, right?
Right.
Oh, this is a solid because all the little hooks got hooked together and blah, blah, blah. We don't even understand, at least I don't know what an explanation of conscious experience from a physical basis would even look like. It's not that I don't know which one is right. I don't even understand how you make the connection between physical properties and subjective conscious experience. Right? That is the hard problem of consciousness. I don't, again, it's not that I just don't know the answer. I don't even know what an answer would be. Okay, that's where we are. You just have to.
Yeah, I understand. Okay, so just one last question, and this will be more of a general one. So there's this question, people sometimes question if philosophy, since its very inception, 2000 and so years ago, has been making any progress. So, I mean, does that question make sense? And if so, what would be the answer?
Well, look, if you clarify the question that you just asked, it not only makes sense, it trivially, all right, the answer is trivial. So let me do that first.
Okay.
2,000 years ago, or more than that, in ancient Greece, as I mentioned, Democritus was a philosopher. He was doing natural philosophy. He came up with an atomic theory. There were other theories, different theories. There were the so-called nature philosophers. And what we would say from a present-day perspective is that what they were doing was proto-physics, was a kind of physics. Yeah? So natural philosophy, and what Newton was doing. Newton, if you ask Newton what was he doing, he would say, I'm doing natural philosophy. Has natural philosophy made progress over 2,000 years? You better believe it has. It made so much progress that physics got spun off from the philosophy department, as it were, into its own department. And people became specialized in what used to be called natural philosophy. So, you see, if you think philosophy covered originally all of these topics, and you ask, did that make progress? It made unbelievable progress. But there's this funny thing that the parts of it that made the most progress got spun off and created their own departments.
Right.
In the university. Again, everybody in the university gets a doctorate in philosophy, right? Gets a PhD. Has there been progress? Yeah, there's been a heck of a lot of progress. Now, then you can ask, yeah, but what about the stuff that is left behind in the philosophy department? So, of course, some of that will be the things that didn't make as much obvious progress, because if they had, they would have gone off into their own departments.
Right.
Some of it stays in the philosophy department for no good reason. Logic has made progress, and logic goes into mathematical logic, and that goes into the math department. You have mathematical logicians, and if you say, has there been progress in logic? Yeah, a heck of a lot of progress. I mean, you think of Gödel, think of all the discoveries think of the discoveries of logic itself, the developments in logical systems. That's made a lot of progress. Has basic conceptual questions in philosophy, have you made progress? Yeah, you made a lot of progress, what's left in philosophy is, of course, tends to be problematic. Because if it wasn't problematic, it would have been exported off somewhere else. And if you then just look at the philosophy department and say, but look, all the stuff in there is really problematic. You say, yeah, but that's not because philosophy doesn't make progress, but because the progress tends to lift things. Then people say, oh, it's no longer philosophy.
Right. I mean, I think that this question arises also because people tend to make these strict separation between philosophy and science, for example.
Well, but that's why, look, if you ask me what do I really work in most of the time, I would say foundations of physics. And if you'd say, well, what's foundations of physics? I would say foundations of physics is a topic that does not have institutional recognition in the university. People working in in foundations of physics, some of them live in physics departments, some of them live in math departments, some of them live in philosophy departments. They're all doing the same thing, right? They're asking the same questions. They're bringing the same resources to try to bear on those questions. Some people have more training in math, some people have more training in straight physics, some people have more training in straight philosophy. To do good work in foundations of physics, you have to know all three and bring them all together. So it's just a fact of institutional life that that this topic doesn't have an institutional place to live. And it lives in a way most comfortably in philosophy departments because they're very basic questions. As I said before, the basic philosophical question is, what is it? And when you ask that in physics, you say, well, what is an electron, after all? Is it a little point thing that's moving around? Is it something that's sort of popping in and out of existence? Is it a kind of cloud-like thing? These are really physical questions, but tend to be asked in philosophy departments. And if you go to the physics department and start asking these questions, and I will tell you, this is a fact, this is not a conjecture, because I had people did it, the physicists after 5 minutes will say, go to the philosophy department, right? Go to a physicist and ask them, well, what really is an electron? Or go and ask them the question I asked. An electron orbital, that picture in your book, what's it a picture of? And I guarantee you very soon they'll say, go to the philosophy department. Not because you haven't asked a question of physics, but because you've asked a question which is not asked in the physics department, a physical question that has been banned from physics, banned from the physics department, right? Not banned from the topic of physics, but kind of banned from the physics department. And the people who ask that tend to end up in philosophy departments.
Mm-hmm. So how do you think it would be possible for us to, at least in people's minds, bridge the gap that many people see between philosophy and science? Because sometimes I even hear scientists claiming that philosophy is obsolete or something like that. So,
Yeah, well, I mean, look, the, famously, physicists have a psychological tendency to be unbelievably arrogant, right? If you watch
yeah,
the Big Bang Theory, these stereotypes are there for a reason. Um, Physicists tend to think they're the smartest people in the world and they have everything figured out and what everybody else is doing is trivial, and it's nonsense, right? It's just complete nonsense. If you go back, I mean, let's weigh on the other side. Einstein complained that physicists didn't have enough philosophical training. Einstein famously, when he was young, they were reading Hume, he was reading philosophers, they discussed it. And he says, that's what you need, a kind of philosophical temperament, or you need to have philosophical ideas and questions to do good physics. And he said physics is going down the tubes because it's lost connection with philosophy. So yeah, you can find physicists who say, oh, philosophy is dead. Those physicists don't read philosophy. They certainly don't read contemporary philosophy. My guess is they don't read much philosophy at all. They haven't thought deeply about it. It's the same way that, a physicist saying, oh, chemistry, that's just applied physics, and biology, that's just applied chemistry, and, we physicists know everything. It's just nonsense, right? It's complete self-serving, ridiculous nonsense. And, people should just stop going along with it. They've been given too much latitude. For 30 years, high energy physics has largely concentrated on doing string theory, which, as we talked about before, looks like it's a complete dead end. And I'll tell you, a bunch of philosophers would have told you 30 years ago or 40 years ago, we don't yet have any evidence that this is correct. And all of this piling on in the theoretical physics community on this one theory, that's a bad mistake, because it may not be right, and there are other things, other ways the world might be. You go back and you'll find philosophers telling you that. So, look, physics had a really great period in the 20th century up until the 60s, up through the development of the Standard Model. You had special relativity, then you had general relativity. You had the development of quantum theory, which at least practically was a great thing. You had the development of that up through the Standard Model, which was finally, the Higgs particle kind of completed that. That was great physics in a certain way. It wasn't great conceptually for quantum mechanics, but it was great physics. But you can't point at fundamental physics over the last half century, and point to anything like that. So I don't think the physicists should be so pleased with themselves, right? The high energy physicists should be so pleased with themselves at the moment.
Yeah, okay, so Dr. Maudlin, let's end on that note. Just before we go, where can people find you on the internet?
You can just plug my name in. I mean, I do have a website at timmaudlin.site. You can, you can go and look. If you're interested in foundations of physics, I'm the director. I founded and direct the John Bell Institute for the Foundations of Physics. That's this guy. And we've got a website where you can again find me and everybody else. If you're interested in foundations of physics, you can find not only me, but a whole bunch of people doing this work from all different points of view and with different disciplinary backgrounds. So that would be something people might find. We have a lot of videos and things that are posted there by different people. So anybody interested in this topic could probably find a lot that they could spend some time with.
Yeah, I will be leaving some links in the description box of the interview. So, Dr. Maudlin, it's been a pleasure to talk to you. Thank you for taking the time.
All right, thank you.
Hello everybody, thank you for watching this interview until the end. My channel is now more than 3 years old, and to keep it sustainable, I would like to ask you to please visit my Patreon page and to consider making a pledge there. If you prefer PayPal, you can also find links to it in the description box of this interview. Otherwise, and if you like what I'm doing, please share it, leave a like and hit the subscription button. This show is brought to you by Enlights, learning and development done differently. Check their website at enlights.com. I would also like to give a huge thank you to my main patrons and supporters, Karen Litzke, Anne Blanchett, Pereira Galarsen, Lau Guerrero, Francis Ford, Hans Frederick Sunda, Ricardo Vladimir, Craig Healy, Adam Castle, Olaf Alex, Jonathan Viss, Elenian Kata, Jacob Klinkby, Matthew Whittingbird, Arno Wolf, Tim Hollis, Henrik Alenius, John Connors, Paulina Barron, Philip Force Connolly, Jerry Mueller, Herbert Gintis, Rutger Voss, Bo Weingard, Rebecca Newberger Goldstein, Dan Demetrio, Robert Windegar, Rui Inácio, Arthur Coe, Zup, Marco Neves, Colin Holbrook, Susan Pinker, Thomas Trumbull, Bernardo Seixas, Pablo Santurbano, Simon Colombo, Jorge Espinha, Phil Kavanagh, Corey Clark, Mark Blythe, Roberto Inguanzo, Michael Stormir, Eric Neumann, Samuel Andreev, Tiago Nunes, Bernard Yugni, Alexander Dunbauer, Omari Hickson, Fergal Cusson, Evan Bodrenko, Hal Herzog, Nuno Machado, Don Ross, João Alves da Silva, Jonathan Librant, Oslam Bullitt, Nathan Nguyen, Stanton T, Samuel Correa, Eric Hines, Mark Smith, J.W., João Eira, Tom Hummel, David Sloan Wilson, Yacila Deza Araújo, Eden Solon, Romain Roach, Dmitry Grigoriev, Diego Londoño Correa, Tom Roth, Yannick Punter, Adana Usmani, Charlotte Bliss, Miran B., Nicole Barbaro, Adam Hunt, my producers, Cesar Webb, Jim Frank, Lucas Stafiniak, Ian Gilligan, Sergio Codriano, Luís Caetano, Tom Vanagdam, Curtis Dixon, João Linhares, Benedict Mueller, Vega Guidi, Sardas France, and Nirban Balachandran. And finally, my executive producers, Michel Rugieski, Rosie, James Pratt, and Matthew Lavender. Thank you for all.